Hello, welcome to this session on cache coherence. Here we are going to talk about coherence in particular, but before that I will touch upon some of those cache policies which has been covered in the previous two videos which are shown here, and I expect those who watch this to go through this two videos before coming here, because I assume that you have already gone through this cache mapping functions like direct mapped cache and fully associative, okay, or set associative. So then design policies, write policies are there, and design elements like how do you decide about the block size and the block size or the line size of a cache, and whether it's a physical cache or logical cache. Those things are discussed in these two lectures, and I expect you to go through them before coming here, because the cache coherence is a bit advanced topic, which builds on what you learned in this previous videos about cache. So what are cache policies specifically for writing into the cache? Because normally writing into cache is more complex than reading from a cache. So there are two wide decisions to be taken by the hardware designer, whether they are going to follow write allocation or read allocation. Means here, what we mean by allocating a block in a cache, okay, is allocation. This is a cache. Do you want to allocate a block or a line into a cache while the processor does a write operation or a read operation? Okay, these two are two different operations which could happen from a CPU for the first time when any particular data element is accessed. It could be for two purposes. When the CPU is accessing a data element, it could be for two purposes, either for writing into it for the first time. Maybe you are initializing a variable for the first time, a value maybe 10. Then you are doing a write operation for the first time, this particular variable which is in the memory. Or you may be reading it. Maybe I have some value there. I am accessing it for reading purpose and adding a value 2 and writing into B. Okay, this variable is now accessed for a read purpose. So there are two possibilities that you are accessing a variable for either write operation or read operation. Now you have an option as a hardware designer whether to allocate a block of memory around that particular variable for a read operation or a write operation, right? Now let me explain about a write allocation. A cache line is allocated on a write miss. Please remember, allocation happens only when there is a miss. If there is a hit, that means it is already allocated in the cache. So only if there is a miss, you decide whether to allocate a cache line for that particular miss, or just directly do the operation into the memory without allocating anything into the cache. So there are two possibilities you have. Now if we decide that we are going to do a write allocation policy, then if there is a write happening to a particular location which is not in the cache, there will be a write miss, and you decide to allocate a cache block for it. Now you may see, you may be coming to the cache looking for a empty block or empty line. If suppose you don't find one, then you have to choose a particular block to be evicted. Then you have a responsibility of writing that particular block into the memory or into the write buffer, and then make that empty and bring a particular new block which you are trying to access it right now into the cache. So that means that executing a store instruction, because you are writing into the cache, means you are writing into the memory, which is done by a store operation on the processor, might cause a burst read. Okay, now what do we mean by burst read? See, there are two ways your memory can be read. One is one address I give, okay, and then I say that I want to read a byte or a word, or maybe 2 bytes or a word, okay, 4 bytes. But you may also do a bulk read. That means I give you an address to the memory and then ask the memory to give me consecutive bytes, maybe 64 bytes or maybe 32 bytes of data. Okay, from starting from that address, you give me all the bytes. So what is the advantage of it? You give one address, and then the memory takes care of incrementing it internally and gives you the block of bytes, contiguous bytes stored in the memory starting from that address. So always the block read is more efficient in terms of time, because the bus transaction takes less time because you give only one address and all the data read from the memory comes one after the other. Okay, there is no time lost between two consecutive data transfer happening from memory to the CPU. Okay, so burst read is a way of reading consecutive bytes from the given address. So there is a line fill. That say whenever you want to fill the cache line, you need to read a block of or a block of bytes from the memory. So you do a burst read before the write is performed. So now you are doing a write allocation. That means you want to actually perform a write operation, but to do the write operation, you are doing a read operation. Okay, because the entire block, maybe you are interested in writing into one particular location in the block, but you read the entire block. So read operation happens first, and then the write operation to a particular byte happens here. Okay, so that's what is meant by write allocation. Whereas read allocation means a cache line is allocated on a read miss. So you don't allocate a cache line on a write. That means what? It doesn't mean that the write doesn't happen. Write happens directly to the memory. Okay, you don't interfere with whatever is there in the cache, because always you say that I my writes will be to main memory directly. Okay, so mostly the write through policies, if it is followed, where the data is written directly into main memory, this write allocation, read allocation is possible, because no, if you find that particular data that you are looking for while writing, if it is already available in the cache, you will have a problem because you are directly going to the main memory by not writing into the cache. So you should have followed write through policy here, so that always the main memory is assumed to be in sync with the content of the cache. So it doesn't matter whether you are allocating a cache line or not for a write miss, because you will always be finding a up-to-date entries in the memory, so you can directly write into it. So in summary, read allocation means you allocate on a read miss. In that case, the write policy must have been write through, because whenever you are reading, you are getting it from the cache, but whatever you are writing is directly going to the main memory. So you are using basically the cache only for the read misses. Whereas write allocation, you do both write and read operations from the cache, and whenever you have a write miss, you allocate one block in the cache. Now let us understand this picture where you have a write back policy, where write back policy says that write updates happening to the cache does not go to the main memory, okay, immediately. It is updated in the data cache. And when do you write into the level 2 system? This is level 2 system or main memory. Okay, that whatever is there in the memory hierarchy, the next level, lowest level is written into. So whenever you are evicting a particular block from the data cache, you write into it. Till then you don't write into the main memory, because all the writes happen only with the data cache. Now what is the advantage? You don't go to the memory or the level 2 system quite often. Now, whenever you are filling it into the cache, and then write dirty data, you are writing into it. Now, there is a presence of write buffer now. So you don't normally write everything into L2 system. Whatever data changes are happening is written into the write buffer, either at the block level, entire block is written into the buffer whenever you are evicting it. Otherwise, you are writing it here. But if you are evicting it, you don't go to the L2 system directly. You keep it in the write buffer, and whenever you have a free time, it will be written. Now, there are two things to be understood. Why is this particular line is given? For the first of all, there is a possibility that when you are trying to evict a data line, okay, a cache line, there is a possibility that write buffer is empty. Now, what do you do? You have, and then one more condition is that L2 system is available to be written into. In that case, what you can do, you can directly write into the L2 cache, L2 level system, and then you can write into the write buffer also for you to access it in case that particular bus block which is evicted is required by the CPU, okay, in the near future. In that case, you can take it from the write buffer directly, okay. So it is also written into the write buffer as well as pushed into L2 level if there is a availability of access of this, and then the write buffer is empty. Why do I say that the write buffer has to be empty in this case? Because all the writes happening from the CPU side, this is the one core. There may be some other writes which are waiting to be written into, and then you are having one more eviction happening. Now this write, okay, from the core side needs to be maintained in the sequence in which the core has written into. The code has written into the memory. So we want to maintain the sequence. So in that case, what you can do is you keep that data in the write buffer if there is a space and then write into it. But if there is an empty case, there is nothing to be followed, sequential writes to be followed, because all the earlier writes by the CPU has been already committed to the next level. So you are free to write it directly there. So in this case, it will happen only when you are using the writes through the write buffer. Okay, mostly all the recent processors have write buffer in it. Okay, now what is the advantage of having write buffer, which has been already explained, that you don't need to wait till the write happen to the L2 system completed, because there may be a delay there, and we don't want to hold the CPU which is waiting for the some line fill to happen. So we want to evict the data cache quickly, as quickly as possible. So you write into a temporary buffer which is there within the CPU, and then fill it fast, so that the pipeline which is stalled because of waiting for this particular data is available in the data cache as quickly as possible. Okay, that's the purpose of write buffer. Now, if suppose you are having a write through policy, that means what it has been already explained, that whatever you are trying to write is not only written into the data cache, it is also written into the write buffer, because always the L2 system writing is not happening directly most of the time, because we don't want to delay the CPU waiting for this write to complete. So we will keep it in the write buffer, and write buffer will be flushed in the same sequence like a FIFO order into the memory whenever the bus is free. Now, some more doubts to be clarified here, which has been already explained. Now, the question was, what is the whether it is a data or instruction cache. If you see there is a dirty bit in the cache, which means that it is a data cache. Okay, instruction cache normally doesn't have a dirty bit, because we don't modify the instructions which is stored in the cache. Now, what is the block or cache size? It is very simple. You see that there are how many lines? Four address bits are there, and then two more address bits are given here, because this is written as a byte, which means that a0 and A1 are the addresses which are possible to take these different addresses, which contribute to 4 bytes of data, correct? Because each address value corresponds to 1 byte of data in the memory, because it's all byte addressable memory. And then you have 4 more bits for the address, which is in summary, there are 4 plus 2, 6 bits. That means 2 power 6 locations can be addressed, which is nothing but uh, the line size, which is 64 bytes. 2 power 6 is 64 bytes. Okay, and then total cache size, how do you compute? Because you see that there are 8 bits which are block index. This is also another name is block index. Now, when you have 8 bits to access the individual blocks in the cache, which can go up to 256, right? 2 to the power 8 is 256. So what is the cache size? How will you compute? 256 into each individual block, which occupies 64 bytes, which is what is given here, which is nothing but 64 by k. And then how many set associative? It is 4 sets are there, because you can see that there are 4 such cache memories are there, which are of 256 in numbers, and because of that, you can say that it is 4 set associative. Okay, so the picture shows that there are 256 cache lines, because chosen by 8 bits, and 4-way set associative. This 8 bits actually refers to a particular cache line. Okay, now this cache line could be either in the top layer or maybe one of the 3 bottom layers. So the same cache line is accessed and looked for each of these 4 layers, and then you will compare the tag value stored in those 4 locations. Okay, you may find this particular block of addresses stored in one of those 4 lines, 4 caches, 4 layers. Then you can say that it is a hit. If none of them have, then you will apply a replacement policy and then identify one victim block to be evicted, and move it to write buffer and bring the new block into the one of those evicted block lines in the four layers. Okay, so that's how set associative behaves, and I hope this is clear. Now, data reads which get a hit in the cache behave the same in both. Why? When you have a data read, if it is getting a hit, it doesn't matter whether you are having a write through or write back policy, because you are not doing any write operation at all. So the cache behavior will be same, right? That's what I am explaining in this. Right, write policy is related to the write operation, but if you are having a read miss, there is no botheration whether you are following a write through policy or write back policy. So that will come only when the write operation is performed on the cache element. Now, what is the eviction line shown here? This is when you have no entries here in the write buffer and you want to evict a particular block, you can directly write into the level 2 system. Okay, and if the L2 system is available, and you will also be keeping it in the write buffer because you may be needing it when there is a write miss. You will look for that particular write buffer. If it is available, you can take it from there. Okay, which is easier. Okay, uh, but that is kept for a later purpose, but actually the memory and the content will be same anyway. If you are writing this content into the L2 system, whatever update has happened, the data cache block has gone out already. So the hardware designers could design to not to have that entry in the write buffer also, because there is no point in maintaining a data which is in sync with the L2 system. Okay, there is no point in again writing this content of the write buffer into the memory system when it is already up to date. So it is a purely a hardware designer's choice. Okay. Now let me make it visible. Okay. Now what we do here, write means there are two ways it can be handled: write around, okay, or allocate and write, which I already explained you. Okay, here allocate and write is used. That means you, when you encounter a write miss and you decide to do a write allocation, then it will be brought into the data cache, and then the data is written into the copy of the data which has been brought into the data cache. Okay, so write policy, copy back, write back policy. When a block with a dirty bit on has to be replaced, what you do is you go through this path. You write into the write buffer first, and then evict it later on. Not eviction, it is called flush it from the write buffer into the L2 system when the bus is free. Okay, it's called, another one is cycle stealing, where the bus is free and the CPU is busy doing some internal operation. You can use the bus to then send the data out. But if there is a write miss, and why are you looking into the write buffer? Because if the data that you are looking for, the block you are looking for, is available in the write buffer, you could take it from the write buffer rather than going to the L2 system, because the L2 system is not up to date with the content in the write buffer. Okay, which is not, if the value, what the block which you are trying to look for, there was a miss, but that block is available in the write buffer, then there is no point in going to the L2 system because it is not up to date. What is there in the write buffer is the up to date value. So you write it back into the data cache, take it from there rather than going to the memory, because memory is not up to date. So that's what is explained here. And I need to do the same thing that I have done. Okay. I'm sorry about it. Okay, fine. So this is visible. Now, you can say that if there is a write miss, the same data could possibly be available in the write buffer, waiting to be written into MM. Those contents have to be taken from the write buffer because MM would have a stale value. Okay, fine. Now we are getting into a new interesting area, cache coherence. Now let me explain this whole thing in one single go. When you are, suppose you are performing a read operation after this write operation, suppose. Okay, now before that you assume that this CPU has already having an initial value v0. Okay, assume CPU 0 reads the value, so you are saying that you are reading that value, so that x is equal to v0 here, and then we assume that CPU 1 is writing a value into v1, and you assume that it was a write allocate. That means even if it is writing into the memory, a particular variable, it is allocated on the cache and then written into it. Okay, so you can assume that write allocation is passed, is what is a policy which is being followed in cache one. So that's why the reason when you are writing into the variable x, it gets a copy into the cache and then its value is written. Now what is happening here in this case? You have x value which is having a v0 here, and then later on it has been updated to v1. Now next, when the CPU 0 tries to read the value x, suppose it has read the value earlier. Now after this has been written, if CPU is trying to read the x value, it shouldn't get the copy what that it has, v0. It should somehow be informed that this value has changed and you better change it to v1, right? Because in time wise, in the time scale, this t1 is trying to read this value. After that, T2 CPU1 has written the V1 value, and T3, when the CPU1 0 is again reading the value, it should see the updated value, not the stale copy that it has. So basically, cache coherence is an issue where you have multiple copies of the same value maintained by different caches in a multi-core system. So the cache coherence is more no, problematic when there are multiple cores accessing the shared variable. Okay. Now, what are the conditions that it could lead to problems? A memory system is coherent. Okay, we call a memory system is coherent when a write immediately followed by a read. Okay, so to the same location by the same process should always get the newly written value. So I have written into a variable x, and then I am reading it in the same processor. Suppose I should get back the value which I have written. Okay, a write immediately followed, a write is immediately followed by a read. You should get the updated value. A read from P2 immediately following a write. This is the example which we shown. Okay, here I am saying P1 and P2. So somebody P1 is reading it, but P2 is reading it, but following a write by P1. That means this is written and this is reading. So you should get back the value which has been written by P1. Okay, latest value. Always the latest written value to a particular memory location should be read by somebody. What if two writes are happening to the same location by any two processes? Okay, so this is also writing, this is also writing. Okay, and um, all the processes are, suppose there are, some other processor px is seeing it. It should always, all of them, okay, px or px1 or whatever, they all should see the same sequence of writes. Okay, maybe v1 was written first and v2 was written second. When somebody is reading it, they should see the v1 first and then v2 next. So the sequence should be maintained. Two writes to the same location by any two processes are seen in the same order by all processes on reading the same location. Okay, I am assuming more than two processes in the system, and then two people are writing into it, and if they are writing in the values in two different time zone time area time values, all of them other processors, when they are reading it, they should see the changes happening in the same order in which these processes have written. So this ensures that the shared location will not have different values or its copies, in different cache blocks. Now you may wonder that, oh, why should I have a cache coherence issue at all if suppose I am having a semaphore, right? And then I am protecting it, and then I am releasing it. What is the issue? Now, even a semaphore, remember, is implemented in the main memory, and there is a requirement from the CPU side that I always see a consistent value. See, always remember, even the semaphore, if suppose two processors, P1 and P2, two cores are running, I will call core because processor and processes may have a similar tone. So core uh, P1 and core P2 are running, and then they are trying to find out whether the semaphore is free or not. Now, what happens if suppose P1 has acquired the semaphore and then modified the value, but they also have a cache? They'll go through the cache. So you may have a copy of the same semaphore value in two locations, two processors in the local caches. So they need to make sure that they both the cores, when they are reading it, they see a consistent value from the memory. So cache coherence is a very minute granular level, whereas Any other critical section semaphore that you are using at the OS is little broader level. Okay, so cache coherence is a problem is happening because the same copy is maintained by multiple processors in different caches, the physical location. They are having the same memory location available there. And even when the process migration happens or multiple processes, maybe they run for some time, the copy is still in the cache, and then context switch happens. Still, you may have the entry because of the previous access of the process. The the entries may be there. So remember the multiple caches in the multiple cores and maintaining different copies of the same data in different caches is caused by the hardware facility that we have provided for easy access or faster access. So when the OS or the process level execution happens, we need to take care of this optimization performance improvement that we have done by introducing caches, okay, which is transparent to the software running. So cache coherence is a problem which is to be addressed irrespective of whether you have mutual exclusion and a semaphore kind of a feature provided by the OS and the software developer are taking care of it, still the cache coherence problem exists. So that needs to be addressed. So there are things you remember why the cache coherence conditions don't appear. Right? Because multiple processes are into the data, process migration happening. Okay, one process is running in P1 for some time, so it would have accessed its own data and mostly data, and it would have maintained it in the cache. And then context switch happens, and the process is moving to some different state, and then they wake up in a different processor, okay, different core. See, core allocation happens by the OS based on which core is available. The scheduler is deciding one of the cache, one of the core in the system to run the process, but the previous copies of whatever has happened with the process is still exist in the other core where this process has run earlier. So unless those copies which are maintained in different caches are synchronized with the memory content, you will have always problem when the migration happens, when the process migration happens from one processor to the another, okay, to another. And IO activities, there may be a memory which is being accessed by the process as well as by the DMA to write into it from an IO, maybe a network card or a hard disk or whatever. So there is a possibility that somebody is writing into it and the processes are reading from it. So there could be a possibility because of IO activity also there will be a mismatch in what the copy is maintained by the CPUs and then what is actually there in the data main memory, because someone has modified it, okay, in the main memory, whereas the processes which the cores which are maintaining the copy of them in their cache may not be even aware of it. So cache coherence is the hardware feature which is the having the responsibility of making sure that multiple copies maintained in different caches internally into the cores are maintained consistently across each of them, and which is in sync with the content in the main memory. That is the main issue that needs to be addressed in the cache coherence. So let me explain the cache coherence and the data types. Okay, you if you have suppose only data which is read by multiple cores, okay, is suppose no is a string, maybe hello world string, which is read by multiple processes running on the different cores. Reading is not a problem at all because you are not going to modify it. So even if you have multiple copies of the same data which is not going to be modified at all, there is no problem, right? It is like taking a photocopy of a book. If you are not going to change it, you can take multiple copies of the same and maintain it, okay? It will be consistent throughout the life of its existence. Whereas if you have a private writable and readable, that means only one process, okay, which is running on one core is going to be writing it. Nobody else is going to write into it or read from it. It's like your own private copy, okay. Then also you don't have any problem unless that process which is privately maintaining its own data is migrated. See, if only one process is going to write into or read from one particular location or not on single location, I'm talking about a block of data, location, and nobody else is going to read from it, then this process is anyway is going to run in one place, right? In that case, you don't need to worry about it as long as it is running from the same core. But The problem happens when this process migrates. When it migrates to another core, you have to make sure that what it has done with the cache here is reflected here, so that when it is taken by this cache is getting the updated value. So there is a problem. Even if there is one single process only is reading it and writing, okay, there is no other processes is going to be accessing it, but still there is a problem when the process migration happens. And then private writable and shared readable. So if suppose you say that I have one data which is only written by one guy, okay, but read by multiple person, then there is a problem, because whatever updates has happened by this process running on one core has to be reflected on all the cores, right? Suppose your parents or your friend is crediting some money into your account, unless you see the changes happening, you will not even get that money there, from the account, right? So anybody writing, one person writing also, it should be reflected on multiple people reading from it, okay? So they will not get the updated value if it is not taken care of. And the most problematic state is where multiple people are writing and reading from the same location or same block of data. This most problematic, okay? All these issues have to be addressed by the cache coherence support that you are going to provide in the cache. Now there are two ways you can solve it. Software is not the only solution, okay? It's not possible to solve the in terms of without the help of hardware. How can you solve it in software? I will say that the hardware software based solutions with some hardware support has restrictions and compromises. Okay, even if I have a software based solution with some hardware support that is required, but there are some compromises. What is a compromise? Shared writable data is not cached. I will say that, okay, if suppose some data is shared by multiple, to be shared with multiple processes running on different cores, I will not cache it at all. So non-cached. In that case, what happens? Whenever I am trying to access that variable or modify the variable, I will come to the main memory and write it. Now, what is the problem that you are going to face? Performance. Because you need to compromise on the performance, because you are not going to cache that particular element at all. That means every write and read, you have to come to the main memory to read it. So, which is not a probable solution. Okay, it's very impacts the performance in a very great way. So no software solution for critical situations. Okay, you cannot solve this by software. So you need to have a hardware-based protocol for all data categories, total but complex. It is effective, but you need to. It's a complex solution, which is going to be discussed in the this particular lecture, and then the subsequent lecture in the which talks about cache coherence protocol in detail. So now let us understand them. Now we discuss hardware-based protocols from three point of view. What are they? How they keep coherence of updated local copies and the main memory. So whatever copy you have here, is it updated in the main memory? Okay. How are you going to make sure that all the local copies are up to date in terms of the content in the main memory? This is called memory update policy. Okay. And then how they, so this is to make sure that whatever you do with the cache is reflected on the main memory, because the aim of the entire thing is you should not stop with only changing the cache content, because it should be reflected in the main memory, which is the actual place where the data resides. Cache is a temporary location, all said and done. Now coherence is when you maintain several local copies, how they are maintained consistent across them. Okay, I told you about private writable and readable from different cores, or both read and writable from different cores. All these kind of situations have to be taken care of. So we will see how they work. Okay, that's going to be the focus. Now, memory write policy, we have already touched upon these two. Okay, how do you update that? Make sure that cache content is reflected in the main memory. There are only two ways: write through or write back. Write through means you immediately reflect it so that it's no more delay there. Write back means there is a lazy writing. You keep updating the cache, and then whenever you are evicting it, you reflect it on the main memory. So these two are the broad level policies maintained for memory update policy. Now, cache coherent policies, there are two things: write invalidate and write update, which we will cover it in the next section. And then how do you interconnect? This is the interconnect. Okay, how you interconnect the cache with the main memory? There are single bus Snoopy cache and multi-stage directory schemes, and many of them. We are going to cover only the Snoopy protocol in the next section, and maybe we'll touch upon this, not in detail, but this is not going to be covered. Okay, so this is in terms of a bus. Now let me just before we end the discussion, what is the uh, significance of the bus as such? Okay, main memory, this I am calling a system bus. Okay, we normally call it a system bus, and it is connected to this, and a cache is connected directly, and then CPU sitting inside. Okay, this is cache and this is CPU. Now system bus means, we always say that a bus is a one which makes sure that serialization of activities with the bus, with the memory, is handled. What is serialization? You might have read about serialization in terms of Java or other um, object-oriented programming cases. Any read writes happening from multiple cores, right? There are multiple cores. Let me call it the C1, C2, C3 are the cores. Then any read operation may be happening, write operation happening. All these things are done if when there is interaction with the main memory happening. They're all done in one after the other. They're serialized forcibly, because you cannot have no two reads, or no one read from this and one write from this, or even any operation in parallel. It cannot happen through the one single system bus. It has to be serialized. Only one person can access the bus and write into the memory. It doesn't matter whether you are writing into this area or different area, but only one transaction can happen over the bus. Burst transaction is something which is again initiated by one single core, but instead of single read or single write, you do multiple bytes. But still, again, this one transaction is happening. After that, another transaction could happen. So serialization is there. Whether you are doing a single read or a burst read, it has to be maintained. That is the characteristics of a bus. Okay, so this is will help you to understand the cache coherence in detail. Okay, when we come to that in the next lecture. Okay, memory update policy, I already told about this. You have a write back policy wherein all the writes are happening only to the cache, and then you write into the memory only later on when this particular block is evicted. Whereas write through policy, okay, write through policy not only updates the cache copy, it also updates the memory. So always the memory is up to date. So you don't need to maintain a dirty bit, because there is while evicting, you don't need to worry about a dirty bit at all, because already you know that memory is up to date with whatever data which is currently there in the cache. So you can decide to evict the cache block instantly. Okay, you don't need to put it in write buffer or later writing and all that, because you are already either, if you are writing the memory, you could do it through write buffer, but not during the eviction. You do it during every write. So you are not going to do a delayed write here. Okay, so a write back policy is a lazy policy, because you are going to delay as much as possible until the block gets evicted. Till then, you are not going to update the main memory. So that's going to be a incoherence, temporary incoherence until the cache block is returned to main memory, is going to be a incoherence there. Okay, the negative sign is needs more complex cache controllers. Now, write back policy, what happens? So data in memory is updated only at some events, which is when data is replaced or invalidated. I will talk about invalidation. Suppose when you are multiple, I'll talk about invalidating a cache with respect to the cache coherence policy. Okay, so a temporary incoherence between the contents in the cache and memory. So it is going to happen. Okay, this is a negative actually. While not updated, okay, read references to memory will be redirected to the appropriate cache. So this is also to be addressed when we talk about uh, cache coherence. So let me explain you what it means by that. Uh, so suppose you have a read from one particular location X, and then that particular location X is available in this cache. Okay. Now what I'm saying is, while not updated, suppose you are trying to read, okay, from this location in this core, and this guy has written something into the same copy of it, which is also here, but the value is also copied here and it is also here. Now, while not updated, while this is not yet updated because you are using a write back policy, so the updated value is here, not in the main memory. Read references. Suppose when you are trying to read from this location, somehow the cache controller sitting here should say that, okay, main memory is not up to date. Please read it from here. Okay, take it from the neighbor. Okay, so read references to memory will be redirected to the appropriate cache. Why appropriate cache? There is only one cache which could may be holding this value with a right to have a rights. Okay, it has a right it has written into that location. Okay, that only that process is core is having the rights to write into the cache, so you have to take it from there. So the cache controller which you need to have is a complex one. Okay, so what is write through policy? It's a greedy policy. Whenever you are writing it, you are going to write into the main memory. So in that case, what happens is when multiple cores are accessing the same variable, you don't need to worry about it. You take it from the main memory because you are not going to have any copy which is not up to date with the main memory. But the problem is you imagine a situation wherein one variable is there, x, which is used only by this core and nobody else is using it. Even still, you will be updating the main memory every write you do. Okay, that's a waste of unnecessary traffic on the bus, which is a negative feature of the write through policy if you are following it there. So I am just explained you write through policy and write back policy in terms of multiple cores coming into the picture. Okay, uh, let us hold on. We are going to go in depth about cache coherence in the next lecture, where all the thing will be very clear, and what are the issues would come up and how to resolve it will be made very clear there. Okay, so these are the following books which you can always try to read about. Okay, thanks for the time. See you. Bye.